Welcome back to the deep dive. Today, we are immersing ourselves in a world where procedural precision is absolutely everything.
Mm,
We're diving deep into high-level disinfection, HLD, specifically the hyper-rigorous process used to clean medical endoscopes.
right. And these are those flexible instruments, colonoscopies, gastroscopies, that sort of thing.
Exactly. They save countless lives, but they are incredibly complex and they're reusable.
That's the key right there. And when you look at the sources we have, these are, procedural manuals, scientific protocols. They make it so clear. The integrity of this process is the only thing standing between a safe procedure and a massive infection risk.
So our mission today is to decode this whole process flow, acting as your guide through this technical gauntlet that every single scope has to run.
Before it's safe for the next patient. Yeah.
And we have to start by establishing the huge difference between just cleaning and high-level disinfection.
Yeah.
Everyone gets washing a dish, but HLD is a completely different beast, isn't it?
Oh, it is. It's not just scrubbing. HLD is a specific chemical process, and it's designed to destroy four very dangerous categories of harmful agents.
Okay.
We're talking about vegetative microorganisms, mycobacteria, fungi, and viruses. If the process works, all four of those threats are neutralized.
Okay, let's unpack this then. Before we even get to the chemicals and the machines, the sources all stress that the prep phase is everything. You can't just put a dirty scope in the disinfection unit and hope for the best.
You can't. The core principle is really simple. If the preparation fails, the entire disinfection process is compromised from the start.
It's like trying to paint a house without sanding it first.
Exactly. The new paint will just peel right off. It's useless.
So walk us through that mandatory sequence. It starts the second the scope leaves the patient.
It begins immediately, right there in the procedure room, with what's called pre-cleaning.
Okay?
Staff have to wipe down the outside of the scope and flush the internal channels right away. This is incredibly time-sensitive.
Why so urgent?
Because if blood or mucus or tissue, they call it bioburden, if that's allowed to dry inside those tiny little channels, the chemicals later on just won't be able to get through it.
That makes sense. You have to get the gross stuff off immediately.
Yeah.
So once it moves to the dedicated scope cleaning room, that's when it gets more intense, right? We hit the first big safety check, the leak test.
The leak test is vital. I mean, vital for the instrument's life and for patient safety. An endoscope is full of delicate fiber optics, electronic parts.
Right.
If that protective sheath is broken, even a tiny bit moisture gets in, and it can permanently damage the scope. But, more importantly, if fluids can leak out during a procedure, they can also leak in during cleaning.
And that would trap contaminants in places the chemicals could never reach.
Exactly. So a failed leak test means the scope is pulled from service immediately.
Okay, so assuming it passes, what's next in the cleaning room?
Next is a really thorough manual cleaning. Staff use these specialized long brushes and enzymatic solutions that are designed for the scope's narrow channels. And then, crucially, after all that work, there has to be a visual inspection.
Looking for what?
Any damages, nicks, scrapes, any missing parts before it can go to the automated unit.
So only if the scope is fully cleaned, passes the leak test, and the visual inspection shows no damages. Only then is it ready for the actual chemical warfare phase.
Precisely. The flow is rigid, preparation, then HLD, then drying, and finally storage. If any of those prep steps fail, it's a complete stop.
Now we get to the chemistry. Once the scope's ready, it enters the disinfection unit, usually called an automated endoscope reprocessor, or AER. And we're talking about really powerful chemical solutions.
Yeah, the sources mention a few, like glutaraldehyde, reproside, hydrogen peroxide. The facility chooses what works best for them, maybe just on ventilation or how fast it works.
But the interesting thing, the really fascinating part, is that the effectiveness isn't just about the chemical itself. It's about its age.
Yes. This is where it gets really interesting, because the chemical's viability is governed by two different time limits that sound similar but are totally different: shelf life and use life.
Okay, break those down for us.
Shelf life is the simple one. It's the standard expiration date on the unopened container. If it expires in December, you can't use it in January, period.
Simple enough. But the use life, that's the one that's like a hidden ticking clock.
It really is. Use life is the effective time the solution stays potent after you've opened the container and put it into use.
Because it gets diluted and stressed by the cycles.
Exactly. By the cycles, by temperature changes, by any tiny bit of organic material that might have survived the manual cleaning.
So you could have a huge tank of this expensive solution, but if you opened it 14 days ago and the use life is 14 days, you have to just throw it all out.
That's exactly right. The protocol demands that when you open a new container, you immediately log the date and your signature right on the container. You started the countdown, and if that use life expires, the chemical is no longer guaranteed to work. It's considered ineffective, full stop.
So before every single cycle, the user has to check both dates, the shelf life on the box and the logged use life on the container itself. A dual safety check.
It is, and failing either one means you stop, drain the entire machine, and you start fresh with a brand new batch. There's absolutely zero tolerance.
Okay, so we've confirmed the solution is fresh and viable. The scope moves into the AER machine, and the physical setup rules here are just as strict.
The setup dictates everything. First rule. The endoscope has to be placed loosely coiled inside the basin. Not bunched up, not tightly coiled.
Why is that tightness such a big deal? Doesn't the machine just flood everything with the chemical?
It does, but if the scope is coiled too tightly, the tubing can create these little contact points, these micro gaps where the fluid can't fully circulate.
Ah, and that's exactly where a biofilm could survive.
Precisely. The loose coil ensures 100% fluid contact on the outside surface.
Then you've got the internal connections. You have to hook the machine up to the scope's channels.
Yes, and this is where you need highly specific parts. The connections have to be secure, and you must use the exact, correct adapter.
Not just one that looks like it fits.
No, we need to stress this. The adapters are specific to the type of scope. You cannot use an adapter for a gastroscopy scope on a colonoscope. They are not interchangeable.
And if you use the wrong one, or it's a little loose,
The pumps in the AER won't create the pressure needed to push the HLD solution through every single one of those tiny internal channels. The cycle will fail, even if the machine's timer says it completed.
that brings us to one of the most eye-opening details in the sources, the micromanagement of the scope itself. For an ERCP scope, the little elevator mechanism has to be positioned at exactly 45 degrees.
That detail right there tells you how unforgiving this all is. And it raises the question, why 45 degrees? Why such a specific angle?
It's all about fluid dynamics. That little elevator lifts tissues and tools during a procedure. If it lies flat, it creates this tiny, protected shadow underneath it.
Where the fluid might just flow over it instead of getting under it.
Exactly. Angling it at 45 degrees forces the disinfectant fluid to clean the underside of that moving part. It guarantees full contact time.
It's proof that we are optimizing for 100% fluid contact everywhere. Inside a channel, on a loose coil, under a tiny mechanical lever, no exceptions.
So once the scope is perfectly positioned, securely connected, maybe angled at 45 degrees, the machine starts. And that brings us to the next critical concept, contact time.
Contact time. This is the duration set by the manufacturer that the chemical has to be in contact with every surface of the scope to achieve the necessary kill.
And the number one rule here is you can never, ever cut it short. If it says 20 minutes, you wait 20 minutes, not 19 minutes and 59 seconds.
Not at all. That time is based on lab tests against the toughest microorganisms, like mycobacteria. Shortening the time, even by a few seconds, risks letting something survive.
But the clock isn't the only thing to worry about. Since the solution is being reused, the user has another check to do, right? They have to check the concentration.
Yes, this is crucial. Verifying the minimum recommended or effective concentration, the MREC.
MREC. Okay.
Think of it like a swimming pool. You have to check the chlorine level to make sure it's still strong enough to kill bacteria. Otherwise, the water looks clean, but it's really a petri dish.
So how do they actually check the MREC?
It's a simple pass-fail test. You take a sample of the solution from the machine's basin, and you use a special chemical test strip. You dip it, and it changes color to show a pass or a fail.
And if it comes back, fail. I mean, the solution is too weak. This is where the protocol gets really high stakes.
It is mandatory. The protocol for failure is absolute. If that strip fails, the entire batch of disinfectant in the machine has to be completely drained and discarded.
Wait, the entire batch? Even if you are almost done with the cycle, you dump hundreds of dollars of chemical and start over.
You dump it all. And the entire reprocessing cycle must be restarted from A to Z from the very beginning.
Why? Why can't you just add a little fresh chemical to bring it back up to strength?
Because you can't risk using a solution that's below MREC. And mixing a compromised batch with a new one? Well, you just introduce uncertainty. And safety demands zero uncertainty.
And the machine itself is tracking all this. If there's any kind of error, A loose connection, a temperature problem, it doesn't just let it slide.
No, absolutely not. The machine will flash an error, it will demand that the user fix the problem, and then it forces a full restart of the entire cycle. It's designed to prevent any and all shortcuts.
So once that full verified cycle finally completes successfully, we're in the post-processing phase. The scope comes out, it's soaking wet. What's next?
It has to be thoroughly rinsed and then dried, and the drying part is also critical. You can't just grab a towel.
Right.
It must be dried with a lint-free cloth, and usually pressurized air is blown through the channels. You don't want any fibers or water droplets left behind.
After drying, it's documentation time. Every single scope gets a tag, and the sources say 4 essential pieces of information have to be on it.
That tag is the scope's passport. It guarantees accountability. It must have the date of processing, the person who did the processing, the date of the high-level disinfection, and the expiration date of that disinfection.
Why is the processor's name so important?
It's the audit trail. If there's ever an issue, an outbreak, you can trace it back to the individual who verified that all these hundreds of steps were followed correctly. And that expiration date on the tag is also vital.
Because the disinfection doesn't last forever.
Exactly, which ties right into storage protocols. We saw that example from one of the sources.
The 14-day rule.
Yes. In that particular unit, their policy was if a scope has been processed but then sits unused for 14 days, you put it through the entire disinfection process again, start to finish, before it can be used. It's an extra layer of caution.
So what does this all mean for you, the listener? The complexity and the sheer rigor required for handling these tools is just enormous. This deep dive really shows that safety here isn't just about the technology. It's about people following an unforgiving step-by-step process perfectly, every single time.
It's a procedural gauntlet. Every step, pre-cleaning, managing the chemical's use life, checking the MREC, the final tag, it's all a critical safeguard.
So to summarize the key takeaways, we covered that mandatory prep sequence, including the leaf test, the vital difference between a solution's fixed shelf life and its time-sensitive use life.
We also talked about the mechanical necessity of loose coiling and using the correct specific adapters in the machine. And of course, the non-negotiable nature of contact time.
And we really focus on that MREC check, understanding that a fail means a full solution replacement and a total cycle restart. No shortcuts.
The level of detail here, following the manufacturer's instructions for use, the IFU, and sticking to every single step, like angling that elevator at 45 degrees, it's just a masterclass in risk mitigation.
It really shows the margin for error is basically zero. A slight deviation, a tight coil, a loose adapter, and patient safety is compromised.
That's it. You have to restart.
Which leaves us with this final thought for you to consider. We've seen how these tiny granular rules governing the disinfection chemistry and the exact physical positioning of parts are critical safeguards in medicine. What other seemingly small, overlooked procedural steps in other highly technical fields, whether it's pharmaceutical manufacturing or aerospace engineering or even large-scale food production, might have equally drastic safety implications if those detailed instructions are not followed precisely as written? Something to mull over until our next deep dive.